Magnifying lenses are something that we're all very familiar with because we use them to read, or we use them to look at small objects like little insects. We're going to talk a little bit about how they work in the context of focal lengths and images and objects. Here's an example of a magnifying lens, one that you use for reading. A magnifying lens turns out to be nothing more than just a convex or a so-called converging lens, one which is bowed outward. Generally, you're using a magnifying lens when you're holding it very close to an object and trying to make it larger in your field of view. Images in magnifiers are upright or not inverted, and so that tips us off right away that in terms of the physics of this, these are virtual images. We generally want with a magnifier for the image to be upright or not inverted because we're using them for reading or for studying an object for which an inverted orientation would be confusing. And of course, the point of the magnifier is to achieve a large magnification, to make the thing look bigger. So if you're doing reading and you can't read the fine print, you use a magnifier to make the print look larger. In this learning module, we're going to address how a converging lens, the thing that normally you think of as giving inverted real images, can then give an upright virtual image to become a magnifying lens. So let's imagine a converging lens. Remember that a converging lens has two focal points. The one in the back is the one that we're used to, and that's the one that light rays get focused to if they come in parallel into the lens from the left. The one that's in the front, though, if you place an object there, that's the one that sends out light rays parallel to the lens on the right-hand side. So that's when, if you wanted to make a flashlight beam, you put a candle right here and light rays come out parallel on the right. Now let's put an object in front of our lens. We'll put it inside the focal length and examine what happens. Light rays come in, and of course a light ray that's coming parallel into the lens focuses to the focal point. A light ray that's going right through the bisector of the lens isn't diverted at all, because the two faces of the lens are approximately parallel. These light rays to an observer look like they're extrapolating back to a common origin. They don't look like they're going to converge at all. In fact, they don't. They never meet one another. But if you extrapolate them back into the lens, they look like they're coming from a common point. Well, that common point is the image. In fact, it's a virtual image. It's not an image created by actual convergence of light rays. It's an image created by the apparent convergence of light rays when you look into the lens, much like we've talked about with virtual images inside of mirrors. The equations which tell us the same facts are none other than our 1 over p plus 1 over I equals 1 over f. Here f is the focal length of the converging lens, which is positive. We can solve this for I by moving 1 over p to the other side of the equation. Now we have 1 over f minus 1 over p. Or 1 over I, if we put it over a common denominator, is p over pf minus f over pf. Or I, if we flip everything, is pf over p minus f. The magnification is always given by minus I over p, and so if we use our previous equation for I and substitute that in, we find that the magnification is minus f over p minus f. And now the question is, when does that get large, and when is it a positive number? Because that's the sign of a magnified virtual image. For a convex lens, which has a focal length that's positive, whenever p is less than f, we will have a few things come true. First of all, I will be less than 0. If you look at the equation for I, when p is less than f, the denominator is negative, even though the numerator is positive. You will also have m is greater than 0, because the numerator of m is a negative number, and the denominator will be a negative number as well. So it will be an upright image. And when p is less than f, the denominator is smaller than the numerator in the equation for magnification. So the absolute value of magnification will be greater than 1. The image will be enlarged. That's how we make a magnifying lens.